Hello, everyone, and welcome to this lecture series on Swivel embeddings for natural language processing. In this first video, we're going to explore the key idea behind Swivel and understand the motivation that led to its development. This Swivel series consists of 4 videos. In this first video, we'll discuss why Swivel was introduced, the limitations of previous embedding methods, and the core idea that makes Swivel different. In the second video, we'll cover the mathematical foundation of Swivel, including pointwise mutual information, or PMI, and low-rank matrix factorization. Then, in the third video, we'll dive into Swivel's objective function and its submatrix-based training architecture. Finally, in the fourth video, we'll implement a simple Swivel model from scratch using Keras. In 2016, Noam Shazir and his colleagues introduced the paper Swivel, Improving Embeddings by Noticing What's Missing. The name Swivel stands for Submatrix-Wise Vector Embedding Learner. The central idea of this paper is quite simple. Instead of focusing only on the co-occurrences we observe in a corpus, Swivel argues that what is missing can also carry valuable information. In other words, Swivel improves word embeddings by explicitly making use of information that previous methods largely ignored. So what exactly does missing mean? Simply put, it refers to entries with a co-occurrence count of 0 in the co-occurrence matrix, that is, word pairs that never appeared together in the corpus. In the paper, these are referred to as unobserved co-occurrences. The key question throughout this lecture is, why should missing co-occurrences matter? At first glance, this may sound like a simple question. However, the answer to this question forms the foundation of the entire Swivel model. Before we answer it, let's briefly review the basic concepts behind word embeddings. As we discussed in the previous GloVe lecture series, word embedding methods can be broadly divided into 2 categories. One category is count-based matrix factorization methods, and the other is prediction-based methods that learn from local context windows. The goal of word embeddings is to represent each word as a low-dimensional dense vector. The linguistic motivation behind this idea comes from Firth's distributional hypothesis, proposed in 1957. It states that a word is characterized by the company it keeps. In other words, words that appear in similar contexts tend to have similar meanings. By learning from these contextual relationships, word embeddings are able to capture both semantic and syntactic similarities between words. Ultimately, building a good word embedding model is about compressing the co-occurrence information contained in a corpus into dense vector representations. And the more accurately and completely we capture those co-occurrence patterns, the better the resulting embeddings become. This is exactly where today's embedding methods begin to differ from one another. Let's start by reviewing the skipgram model in Word2Vec. The objective of skipgram is straightforward. Given a center word, also called the target word, the model tries to predict the surrounding context words. To do this, it scans through the corpus using a sliding window. As it moves through the text, it continuously generates pairs consisting of a center word and one of its neighboring context words. These word pairs become the training examples. However, computing the full softmax over the entire vocabulary is computationally very expensive. To overcome this problem, Skipgram uses a technique called negative sampling. Instead of comparing the target word against every word in the vocabulary, negative sampling trains the model using two types of word pairs. The first type consists of positive pairs, word pairs that actually appear together in the corpus. The second type consists of negative pairs which are generated by randomly sampling words that did not appear in that context. By learning to distinguish positive pairs from negative ones, the model efficiently approximates the original softmax objective. During training, positive pairs pull their embedding vectors closer together in the feature space. Negative pairs, on the other hand, push their embedding vectors farther apart. This simple training strategy turned out to be remarkably effective and played a major role in the success of Word2Vec. However, it also has an important limitation. Because Word2Vec learns only from local context windows, it never directly models the global co-occurrence statistics of the entire corpus. In other words, it captures local contextual information very well, but it has limited access to the broader statistical structure of the corpus. Now let's briefly review GloVe. Unlike Word2Vec, GloVe begins by collecting global co-occurrence statistics from the entire corpus. Instead of learning directly from local context windows, it first builds a co-occurrence matrix that records how many times each word and context word appear together throughout the corpus. Once this matrix has been constructed, GloVe learns word embeddings by approximating the logarithm of the co-occurrence matrix. More specifically, it uses a weighted least squares regression to approximate the logarithm of the co-occurrence counts. Word pairs that co-occur frequently receive larger weights, while infrequent pairs receive smaller weights during training. By taking advantage of global co-occurrence statistics, GloVe achieved excellent performance and became one of the most influential word embedding models. However, it also has one important limitation. Word pairs with a co-occurrence count of 0 are completely excluded from the objective function. In other words, GloVe defines its loss only for observed word pairs. The enormous number of unobserved pairs simply do not participate in training. This limitation becomes the starting point of today's discussion. Before we move on, there's an interesting theoretical result that connects Word2Vec and GloVe. In 2014, Omer Levy and Yoav Goldberg showed that skipgram with negative sampling, or SGNS, can be viewed as implicitly factorizing a shifted PMI matrix. This was an important discovery. Although Word2Vec is usually described as a prediction-based model, it turns out that mathematically it is closely related to matrix factorization. This observation inspired a new line of research. Researchers naturally began asking, if SGNS implicitly factorizes a shifted PMI matrix, why not factorize a PMI matrix directly? This idea eventually led to models such as GloVe and later Swivel. Next, let's turn our attention to sparse matrices and the meaning of zero counts. When we build a co-occurrence matrix from a large corpus, we find that it is extremely sparse, with more than 99% of its entries typically being 0. At first, it may seem that all of these zeros mean the same thing, but they don't. In this example, entries with counts greater than 0 represent observed co-occurrences, while entries with a count of 0 represent unobserved co-occurrences. The zeros along the diagonal correspond to a word paired with itself, so they are not considered during training. The remaining zero-count entries can actually arise for two very different reasons. The first case is when two words are semantically unrelated, so there is essentially no reason for them to appear together. The second case is when two words are actually related, but the corpus is simply not large enough for their co-occurrence to be observed. For example, looking at this co-occurrence matrix, we can see that the count for fun and love is 0. However, this does not necessarily mean that these two words are unrelated. The co-occurrence may simply have been missed due to limited corpus size. This distinction is extremely important. Unfortunately, both Word2Vec and GloVe treat these two kinds of zero-count pairs in essentially the same way. GloVe simply ignores them. Since zero-count pairs never appear in its objective function, the model learns nothing from them. Word2Vec does make partial use of unobserved pairs through negative sampling. However, this is only an approximation based on random sampling. It does not systematically distinguish between word pairs that are truly unrelated and those that simply happen to be unobserved. As a result, an important piece of information is lost. This problem becomes even more serious as the vocabulary grows larger or when the corpus is limited to a specific domain. In those situations, many zero-count entries are caused simply by data sparsity rather than by true semantic independence. The problem is especially severe for rare words, technical terms, and newly emerging words, since they naturally have much fewer opportunities to co-occur with other words. This is one of the fundamental limitations of existing embedding methods. And this is exactly the problem that Swivel was designed to address. Now let's summarize the key idea behind Swivel. If we think back to the title of the paper, Improving Embeddings by Noticing What's Missing, the message becomes quite clear. The central idea of Swivel is to explicitly model unobserved co-occurrences, rather than focusing only on the word pairs that actually appear in the corpus. This represents an important shift in perspective. Instead of learning only from observed data, Swivel also learns from what was not observed. The key insight is that even word pairs that never appear together may still contain valuable information. In other words, the absence of a co-occurrence can be informative, and that information should be reflected in the learned embeddings. To achieve this, Swivel uses two different loss terms. Observed word pairs and unobserved word pairs are treated differently during training. This allows the model to learn effectively from both observed and unobserved data. We'll examine these two loss terms in detail, along with the mathematical formulation, in the third video of this series. The entire approach is built on a principled statistical framework based on PMI and low-rank matrix factorization. We'll cover the intuition behind PMI as well as the mathematical details in the next video. At this point, I'd like to emphasize one important idea. Swivel is not simply another engineering trick designed to squeeze out a little more performance. Its motivation is much deeper than that. Co-occurrence statistics collected from a corpus inevitably contain uncertainty. Sometimes two unrelated words may happen to appear together a few times purely by chance. On the other hand, two genuinely related words may never co-occur simply because the corpus is too small. Rather than ignoring this uncertainty, Swivel attempts to account for it during training. In other words, it treats the inherent uncertainty in co-occurrence statistics in a more principled and statistically meaningful way. Next, let's summarize the three embedding methods we've discussed. First, let's compare their training styles. Word2Vec is a local context prediction model. In contrast, both GloVe and Swivel are global matrix-based methods that learn from co-occurrence statistics collected across the entire corpus. Next, let's look at how they handle zero-count pairs. Word2Vec makes partial use of them through negative sampling. GloVe simply ignores the zero-count pairs. Swivel, however, explicitly models unobserved co-occurrences as part of its learning objective. Finally, let's compare their scalability strategies. Word2Vec learns directly from the corpus without constructing a global matrix. GloVe requires the entire co-occurrence matrix to reside in memory during training. Swivel addresses this limitation by dividing the matrix into shards or blocks, allowing the model to scale much more efficiently. We'll briefly discuss this shard-based training architecture in the third video. In this video, we started by reviewing the fundamental idea of word embeddings. Then we revisited both Word2Vec and GloVe, highlighting their strengths as well as their limitations. We also explored the two different meanings of zero-count entries in a sparse co-occurrence matrix and saw why treating all zeros the same can lead to the loss of valuable information. Finally, we introduced the central idea behind Swivel, explicitly modeling unobserved co-occurrences to make better use of the information contained in the corpus. If I had to summarize today's lesson in a single sentence, it would be this. Not all zeros in a co-occurrence matrix are the same. Even unobserved co-occurrences can carry valuable information. In the next video, we'll build the mathematical foundation behind this idea by introducing pointwise mutual information, or PMI, and low-rank matrix factorization. Thank you for watching, and I'll see you in the next video.